First, we should ask, what is a system? Yeah, exactly. Two or more equations graphed on the same graph. And so what does it mean to solve a system?
Give any number that will its intersection.
Yeah, all the intersection points. Find all those intersection points. Now, if that's visual, what are those intersection points going to do to your equations?
Make them correct.
Yeah, we're going to make them all true. So that's what you're looking for, is a coordinate that makes all of your equations true. All right, and then what is the formula for the inverse method? So let's say that we had a system, and I'll just make it something simple like negative 2x plus 3y equals, equals.
Did you make the marker darker?
5. Yeah, I know. Seriously, that.
Oh, barely the second one.
Okay. Negative. There we go. Negative 2x plus 3y. But I like the question, can I make the marker darker? Like, no, couldn't. So negative 2x plus 3y equals 5. And then if I have another system like 8x minus 2y equals negative 11, then you wrap the first set of coefficients with the variables in one matrix, negative 2, 3, 8, negative 2. You wrap the answers in another matrix, and you call it B. And then you use your calculator to type in A inverse B. And this is wonderful. Okay, so let's just say it gave us the answer 3, 7. What do the numbers 3, 7 represent?
X and Y?
Exactly. X and Y in the order in which they originally appeared. So X is 3, Y is 7. Now, what's the only time this isn't going to work?
Is it if there's more? Is it like there's or like that it's if it's inverse of the two of them or the same one? Or it's 1, 0, 0, 1.
Well, that's a matrix times its inverse will equal 1, 0, 0, 1, and that's okay. When will your calculator not produce a point of intersection?
When it's intersect.
Right, if they don't intersect, right? So A inverse, your calculator might give you a calculator error and say, actually, that inverse doesn't exist. And that error will exist if your lines are either parallel or overlapping. Okay, so this inverse method will work with 3 equations, 4 equations, 5 equations. It'll work so long as there actually is a single point of intersection that makes all the equations true. If there's not a single point that makes all the equations true, then this matrix method won't work. Okay, and then finally, how do you solve a nonlinear system? I think we finished all that last time, where we did these nonlinear systems either by substitution or elimination, and then we graphed the inequalities and actually looked at regions of space that were double true. Okay, so we finished all that? Okay, so folks, I think we're ready to move along and start chapter 9. Very exciting, chapter 9. It's a different kind of chapter, and it's about sequences of numbers. I think that you'll enjoy it. It's kind of like puzzles, okay? Like puzzles, you're sitting on your plane, and you have nothing to do, so you bust out a riddle book or a puzzle book. That's a little bit of what we're going to do. Now, so here's our calendar. I can't find our calendar. There we go. So today's April 22nd. This week we're doing chapter 9. Then next week on Monday you're taking your test. I already put the practice test and the solutions on Canvas. I'll bring the practice test for you next time. I think that's it. So did I tell you the wiener dog joke? I didn't? Why did the cowboy get a wiener dog?
Why?
He wanted to get along, little doggy. Get along, little doggy? That's a phrase. Okay, how does NASA organize a party? They plan it. They plan it.
Oh, they plan it.
All right, what'd you say, Hector?
They put it on a car.
They put it on a car.
Yeah. Wait, you said NASCAR or you said
NASA.
Oh, okay, never mind.
Yeah. I'll tell these 2 jokes on Wednesday. All right, so I think we're ready to go. Because in the last class, somebody reminded me that I said that I would take questions on homework, but then I didn't. So what of any questions would you guys like to ask about homework? Does anyone have any questions off the top of their head? Now keep in mind, it would be really convenient if you folks, while you're doing the more homework, started emailing me saying, hey, do this one in class. You know, you could email me and say, I need help solving this one. Or you can just email me and say, hey, please do this one in class. And then that would give us a list of problems to do. Because right now, I'm like, well, I don't know what problems I should do. Should you guys have a recommendation for which ones we should do. So if you start emailing me, then we can do that. So, same question. Does anyone have one that you'd like to see done?
I do.
So we're done with chapter 8 then, and in chapter 8, we've got just sections 8, 1, 3, 4, and then 7. Because I took away determinant and Kramer's rule, so that's not in there anymore.
Yeah, I was gonna ask about that.
Yeah, somebody emailed me and I took it out. Because we didn't do it in class. So, one more time. Anybody have any questions you want to ask? Like, okay, I just went into section 8.7. What?
She said she had a couple problems that she couldn't figure
No,
out.
are you, I want to remember.
Yeah, the question is if anyone remembers it. All of these systems look pretty similar to what we've done. That one looks fun. Like this one, we didn't necessarily do one like this. It says pick the two inequalities so intersection is the region shaded. So what we have is a parabola shading down and a line shading up. So I need a parabola shading down. This is the only parabola that's shading down because its y is less than, so that's down. And then I need a line shading up. That means I would need y is greater than. And this is the only inequality that shows y is greater than. So I believe that's the answer. Yeah. Number 6 is kind of clever. Shall we try number 6? It just says that a rectangle has an area of 228. So that means base times height is 228. But then I also know that the perimeter is 62. So that means that, oh, does anyone think my labeling of my rectangle is kind of funny? I put height on the sideways one and base on the, does it matter? No. Is it confusing? Yes. Okay, so now that means that h plus h plus b plus b is equal to 62. So that's 2b plus 2h equal to 62. So how do we solve this system? Can we do elimination?
Yeah.
What? We can? We can only do elimination if you have x's stacked on top of x's and y's stacked on top of y's. And this is b times h being multiplied. So we definitely can't do elimination. I know that elimination is your go-to, but in this case you can't because the variable's being multiplied.
You divide h or b on both sides.
You could move the b over or move the h over, that's true, and then you'd have a single letter. Or you could solve one of these. I think in the end I would solve for one of these. So I'm going to move the 2h over.
It'll be easy.
Yeah, I think so too. So then I have 2b equals 62 minus 2h. And if I divide everything by 2, then that gives me b is equal to 31 minus h. And now I take that and I plug it in for b. So now I have h times b equals 228. And then I have, for b, I have 31 minus h equals 228. Now everybody, from right here, you can kind of see what's going to happen next. Like, it's very not exciting. You're going to distribute, and you get 31h minus h squared. You're going to move all of your terms over to one side. Since this is a negative h squared, I'm going to move both of these over to there. So I'm going to add my h squared over. I'm going to minus the 31h over. And then I'm going to end up with 0 equals h squared minus 31h plus 228. And then from there, I need to factor it. So I'm looking for a number that multiplies to make 228. Oh, man. What multiplies to make 228? 1 and 228. 2 and 114. 3. Yeah. 3 and 76. Okay, 4. Yeah. 60. 57. 5. No. 6. 6 and what is it? 38? 7? No. 8? No. 9? No. 10? No. 11? No. 12? Yeah. 12 and what is it? 19? Okay. Oh, it did not produce the. Oh, it did produce the answer.
Yeah.
What multiplies to make 228? That adds to make negative 31. Yeah, it would have to be a negative 12 times a negative 19 makes 228. And when you add them, you get negative 31. So now you have h minus 12, h minus 19. And therefore, by the zero product rule, we have
the height is either 12 or 19. Can it be either? You said no awfully quickly. It can't be both?
Well, he's already.
Let's find out. If h is 12, then b would be 31 minus 12, which is 19. So that means that if h was 12, then b would be 19. That's one possible answer. But if h is 19, then b would be 31 minus 19, which is 12. So then if h is 19, then b is 12. So what did that do? It's either 12 and 19 or 19 and 12. So what does that mean? Yeah, it's either this or it's this, right? Depending on what you call base and what you call height. Is that two different answers? I mean, not really. It's just a rectangle that's been rotated, right? I mean, you could call it two different answers.
What happens if you put it in there?
That's a good question. What happens when we put it in backwards? It says here that it doesn't specify which is length and which is width. So what should I do first? Should I do 19 and 12? Anyone want to bet any money?
Oh, I need to be both right.
I'll bet a penny that it's going to be right. Boom! Okay, now, what if I put in 12 and 19? I'll bet 2 pennies that it's going to be right. Oh!
So I can
Oh.
decipher which one's which.
Now, hold on a second.
Oh, it says it right there.
It says it right there, where length is greater than width. So that's why it's got to be that way. There we go. So see, that was interesting. 12 and 19, they both are technically correct, but they had this random little statement here that says that they want the length to be greater than width. Okay, well, that's no problem. Now, folks, I want you to notice something. From get-go, if we had simply made the assumption that we have a rectangle whose area, so watch, the area is 228, but the perimeter is, what was it, 61? And therefore that led to the idea that, was it b is 31 minus h? And notice what that means. If I add the h over, that means h plus b is 31. So look what we have. I'm looking for two numbers that multiply to make 228, but add to make 31. I'm looking for two numbers that multiply to make 228, but add to make 31. It automatically is the answer. Just by doing a factor table, you find two numbers that multiply to make 228, but add to make 31.
I have a matrix numbers question.
Oh, did you have another one for more?
Yeah.
Yeah, okay, go ahead.
What about this one?
What section?
8.4.
Okay,
Question 8.
great. This is wonderful. Thank you, Hector. So solve the system. Now right here, they don't really tell you, what approach to take. You could take an elimination approach or a substitution approach, but it is in the section called matrix inverses. So theoretically, you would just write this down as a matrix. So first of all, folks, notice they gave you the letters kind of out of order. So you need to put things down in order. And I'm going to start by making a grid where I'm going to very carefully put my numbers in order. And then b equals the answers. So the first equation is already x, y, z. So it goes 3, -6, 1. And the answer is 12. The second equation, x, y, z, okay, it's still in order, x, y, z. So that's -1, 1, and -1. And the answer is -3. And the third equation is just x, y. So that's 1, -2. What's z? 2. Yeah, 0. Okay, Hector, that's what would go into your calculator. And then in your calculator, once you have all that inputted, you would simply compute A inverse times B. And that is going to give you the answer, whatever it is. What? Oh, right. Well, I mean, in any case, you're still going to do the same thing.
Yeah.
Yeah, so you just type it into your calculator and it will do it for you. That is assuming all 3 lines go through 1 point. Keep in mind that for 3 lines, actually it's 3 planes to go through 1 point. That means all 3 planes, actually, I can still talk about it in terms of lines. It's only going to give you an answer if all 3 lines actually went through the same point. Keep in mind that's very specific. 3 lines all going through the same point. It could be 2 lines and 1 going through both. It could be none of them sharing, more than 2 points. So out of all the possible ways that 3 lines can intersect, what are the odds that you're actually going to get a solution? There are lots of ways that that matrix might not be real, that it might not actually compute anything. It's kind of hard to give a percentage.
huge.
I mean, I guess what we're saying is if you just fill this thing in with random numbers, I mean, in theory,
You can get something out, but
should it be 1 out of every 3 times? Should it be 33%? I don't know. That's a good question. I mean, there's only 3. Ooh, the lines could look like this too. So does that make it 25%? I don't know. I don't know, but not very good. Okay. Any other questions from the homework?
Yes.
Great, Emily.
Section 8.1,
Okay.
question, last week, 16.
16. All right. This one right here.
Yeah.
Okay. So we're gonna take a look. Now, first of all, folks, this is fun. So far, 2 of you have asked me a question. This is wonderful. And so my encouragement to you is when you go home, email it. Email it. Email me a couple times a day if you want to. I'm very happy to get emails from you folks. It gives me something to do. All right. So we have a movie theater with a seating capacity of 323. The theater charges 5 for kids, students, and adults. Half as many adults as children. The total ticket sales is 2,342. So how many kids, students, and adults? So what's the first thing we do? Define our variables. All right, so first we'd say let, and we might as well do x, y, z. So x is number of children, y is number of students, and z equals number of adults. We're not letting old people into this theater. Although I guess that's just an adult, huh? Okay, so what's our first equation? What's our first piece of information they gave us? Yeah, the total seating capacity is 323. So our equation is?
X plus y plus z is 323.
What's the second equation they gave us? There are half as many adults as children. Now, this is the part that can be tricky. How do you turn that into an equation? And I start by making a table of values. There's half as many adults as children. So here's the children, here's the adults, and there's half as many adults as children, so I'm just going to start making things up. If there's 10 children, how many adults are there? And if there's 20 children, how many adults are there? And if there's 14 children, how many adults are there? Now, do we all agree that that's the order that it should go? There are half as many adults as there are children. So if I call this x, what would this one be? Hold on, let me be consistent. Children was x, that is actually x. Right, but what were we doing? Dividing by 2. So what that tells me is that if children is x, which it is, then adults, even though we're saying adults is z, it's also half of x. So now I know that half of x is equal to z. Now that's only one way to write the equation. I could have easily said, let this be 2x, because then it's easier to divide it by 2. Half of 2x is x. But my variable for children is x, so I shouldn't do that. But I should say 1/2 x equals z. But now that I have 1/2 x equals z, I can multiply both sides by 2, and I can get an easier equation, x equals 2z. So it's totally up to you. You can either use the equation 1/2 x equals z, or you can use the equation x equals 2z. So in any case, there's my next equation. So x equals 2z, I'm going to use that one, because that's a nice substitution sentence. And the last equation, total ticket sales, 2342. So how do I do that? It's total ticket sales, which is talking about money. And remember, there's always going to be an equation where you multiply everything. So that would be, what, 5x, 7y plus 12z equals the total dollar value of 2342. So those are my equations. Now, what they want you to do right here is substitute. They want you to plug 2z in for x everywhere you see it. And notice if you do, if I plug 2z in for x, then this first equation becomes 2z plus y plus z equals 323. And then you can combine like terms and you get y plus 3z. Notice it's just a 2-variable equation. And then in the bottom one, if I plug in 2z for x, then that's 5 times 2z plus 7y plus 12z equals 2342. And again, I can combine like terms. 10z plus 12z is 22z. So you'll notice that philosophically, we once again reduced a 3-variable, 3-equation system into a 2-variable, 2-equation system. So now I can solve for y and z using any method you like. You could do elimination. I multiply this by -7, So then I have negative 7y minus 21z equals 7 times all that. And that gives us 7 minus 3.3, which is 2261, but it should be negative. There we go. So now the y's cancel out. And look at that, z equals 2, 3, 4, 2, 1, 2, 3, 6, 1. And the number of z is 81. So z is the number of adults, there are 81 adults. Now notice, folks, another thing you could have done is put it in matrix form and solve it with a matrix. So I'm going to rewrite x equals 2z. Instead of x equals 2z, I'm going to move the 2z to the left where it should be. And then I have x plus 0y minus 2z equals 0. Is that fair? Do you see why how I did that? Because now I have 1x plus 0y minus 2z equals 0. And instead of that equation, I have this equation. And now I can type all that into a matrix. And I can have my calculator do it for me. So I would say A equals 1, 1, 1, 5, 7, 12, 1, 0, 2. And B equals 323, 2, 3, 4, 2, 0. And now my calculator will do it for me. So I realize in this section you're supposed to be doing elimination. But in this section you could use your calculator to check your answer and should get the same answer. Oh, right, yeah, you have to do A inverse and then A inverse. Okay, Emily, you asked about this one. Did I answer your question?
Yeah.
Oh, good. All right, folks. I invite you to continue emailing me. That would be most helpful if you email me. Even if all you did was message instructor, hey, yo, let's do this in class. And then you send it to me, and then I'll know, like, oh, good, that's what that you want to see down in class. Okay?
So kind of for section 8.7, the last question, because those ones where we're going to like figure out what's like the shaded in parts.
Yeah, I did this one at the start of class. And so we're looking for a parabola shading up or down. From the parabola, is it shading up or down? Up. So it should be y is greater than. So I go to the parabola, and this is y is greater than x squared. This one is not. This is y is less than x squared. So that's wrong. So there's my parabola, and it's the line shading what? From the line, it's shading up or down? Down. So I go to wherever the y variable is, and it better be y is less than. So it'd be this one. Notice that you don't even have to finish solving for y. So long as y is on the less than side of the equality sign, then it's going to be shading down. In any case, that's the answer. So, Hector, did I answer your question? That's how you want to think about it. Okay. Really nice, folks. Well, that's the more homework.
One of these equations on the test?
What?
We're running one of these on the test?
No. All right. So, folks, we get to start sequences today. By the way, Lee, somebody told me that they were doing homework with you, and then they got to one. Oh, it was Celine, where the format of the answer was surprising and not what you expected. And so I asked her if she could tell me what the problem was, but she said she didn't remember.
Yeah.
So maybe you can remember. Maybe take a look around and tell me we're break.
Okay.
Or not, you know.
But see, again, in a situation like that, you or Celine, if you had said message me, then you could say, hey, let's look at this later, and then I'd know which one to do.
All right, folks, we're looking at sequences. This is pretty fun. I gave you some examples here to look at. Oh, where's my mouse? I don't see my mouse. Here we go. Don't I still have my mouse?
Next time I'll just note it down. Because
Yeah, just write it down next time.
Oh, now I know. There. Okay, so there's my warm-up questions. Now, folks, I want to put us in the right mindset right up front. These are puzzles. They're riddles. They're problems to be thought of like you're on an airplane and you don't have anything to do, so you bust out a riddle book and you start trying to solve riddles. Do any of you do that?
No.
Wait, I kind of do that sometimes, but it's
Well,
not
do you ever
it's
do
not like
puzzles?
that. I use there's like this wooden ball that I have. It's
Okay.
basically like a puzzle in a box. I like
Sure.
puzzles.
Yeah, puzzles. So that's what we're thinking about here. So take a look at that first problem. I say, what is the next number in the sequence? 1, 2, 4. So what is the next number in that sequence?
6.
I hear the claim of 8. Why is the answer 8? Yeah, perhaps the answer is 8 if you're multiplying by 2 every time. Perhaps. What else could it be?
Adding by 2, let's see.
16. That would be interesting, potentially. Why 16?
Or,
Yeah, I mean, 2 squared is 4. 4 squared is 16. You're really close there, Dave. There's something there. It just didn't describe every single number. Hector, I heard you say 6.
yeah, because it could be adding 2.
Yeah, if it was adding 2, then you could keep on adding 2, but the first one was adding 1. So, you know, this lays open the question, what do we mean by a sequence? Does it have to be the exact same rule every single time? Or are you allowed to just change things as you go?
It's like multiplying or adding, subtracting.
Right. It just depends on what you allow for a good pattern. Because, like, you know, just imagine I'm like a 5-year-old toddler. And I'm like, guess the next number in my pattern. Go ahead, guess the next number in my pattern. And then, like, you're looking at it like, shit, I have no idea. And the kid's like, well, you know, you add 4, then you times 5, then you subtract 3, then you divide by 4. Like, yeah, that's not a pattern. You're just doing things. Totally different, not a pattern. So we have to agree on some ground rules about what we even mean. And typically, at least in this class, we're talking about where you're doing the exact same thing every time. And even more specifically, it's either multiplication or addition. Now, to be fair, that doesn't mean we're not talking about division and subtraction. Because what we could do is if I had the pattern 5, 10, 15, 20, then that would be me adding 5 each time, right? But I could have the pattern 20, 15, 10, 5, 0, -5. And you can say, well, you're not adding, you're subtracting. And that's true, I'm adding -5 each time. So whether you're adding a negative or adding a positive, or whether you're adding a number or subtracting a number, we're still going to call that valid, because you're doing the same thing each time. Likewise, you could multiply over and over again. So like you could have 1, 2, 4, 8, 16, and that's multiplying over and over. Or you could go 8, 4, 2, 1, 1/2, 1/4, and so on. And what you're doing is multiplying by 1/2 of the time. And multiplying by fractions is the same as dividing. Okay, so our ground rules are that a pattern is a pattern if you're doing the same thing every time. So therefore, in the case of 1, 2, 4, it seems like the answer's got to be 8. But just to be fair, if you relax your definition a little bit, could it be 7? Did anyone think 7? How would you get 7? That'd be +1, +2, +3, +4. Does that seem like an acceptable pattern? I mean, it sure seems, it's certainly better than the 5-year-old toddler pattern. I mean, at least you're progressing in a way that's obvious. But you're not doing the exact same thing. Okay. All right, so that's the first pattern. This next one is a true puzzle. I almost feel bad telling you the answer, because it's such a good one. You're going to want to do this with your friends and family and on your next first date. So what's the next number there? It is 50. Why 50? Well, 1 times 2 is 2, 5 times 2 is 10, 10 times 2 is 20, 25 times 2 is 50. A couple of those things you've multiplied by 2. Doubling is the same as multiplying by 2. So, I mean, we did double that one, but we certainly didn't double 10.
Multiplying by 5, and then subtracting.
And maybe multiplying and subtracting. I mean, there's a lot of complex things we could be doing now. I think subconsciously, you probably all know the answer. Subconsciously, 50 came to mind probably pretty quickly. You all recognize these numbers, what? 1, 5, 10, 25. Did you want to take a guess?
Oh, I got it. Quarter, it's money.
It's money. That's it.
Oh.
Penny, nickel, dime, quarter, 50 cent, silver dollar. Anyway, that's the end of the pattern. The numbers don't keep going because we only have so many denominations. Do we have a $2 coin? Was there ever a $2 coin? Well,
we have a
there's
$2
bill.
bill, but I don't know.
I don't know about a $2 coin. That's kind of cool.
I've never seen the.
I found it online, I don't have one.
Okay. Well, I believe you in any case. I have no reason to doubt it. Okay, so those are some patterns. Now, what about finding the sum of numbers? Okay, so first of all, what we're doing in this chapter, which is this week, today and Wednesday. First, we're just trying to understand what the pattern is and the ability to predict the next number. That's key. So to be able to find out what is the pattern and what's the next number, or better yet, what's the 100th number, right? What's the 100th number down the line? And ideally, you wouldn't have to actually get there. Like, that would be really lame if you actually had to sit there and write them all out, 67th term, 68th term. I mean, that would take forever. You'd like to just have a formula that says, whammo, that's the 100th term.
Okay, so like a n equals 2n plus 1, and for the first column for the 0.9 set of assignments or more is find the first 10 terms of the sequence.
Yeah, exactly. So that's the type of problems that we're interested in, is given a sequence, find the rest of the terms and find any given arbitrary term. Okay. The next thing we're going to want to do is add things up. So if I did give you a sequence, like this is obviously just all the counting numbers from 1 through 100, what's the sum of all those numbers? Or here I'm adding together all the fractions that have been multiplied by a half. So half of a half is a fourth, half of a fourth is an eighth, half of an eighth is a 16th, and so on. What happens if you add all those up to infinity? So we want to look at finite sums, and we want to look at infinite sums. So this is my first challenge problem to you. And I'll tell you a story. This is about a mathematician in the 1700s. His name was Carl Friedrich Gauss. And he was a little boy in school, maybe 6 years old, in preschool, first grade, I'm not sure. And the teacher wanted to leave the room temporarily. So the teacher put a question up on the board and said, here you go, little boys and girls. Everybody sit down and figure out what the sum is. And the teacher figured this will keep them busy for a while. I mean, these are first graders. It's going to take them forever to do this. I can leave the room and go do what I need to do and come back and we won't hurt each other. So anyway, before the teacher even had a chance to get up and leave the room, old Gauss came over and was like, the answer's 5,050. And the teacher's like, Gauss, you little pain in the butt. First of all, you cheated. I don't know how you got the answer, but go sit down and don't say anything, right? So that's the story about Gauss. So how do you add up all these numbers? What's one way to add up all the numbers? Yeah.
So
Yeah,
if you could type, usually type in the start with like the biggest number in scope. Adding small.
What do you mean you start with the biggest number? Do 100,
100, 100, 199, 100, and well.
Okay, yeah, so you just have to type it in your calculator. Now, do any of you want to type all the numbers in your calculator? You can try to do in chunks, by all means. Yeah, there's a lot of ways to do it, that you can chunk up the information.
All right, 175, chunk it up.
What, did you say 175? Oh, you mean 100 through 75?
Yeah, chunk it up out of there, and
You
then
could chunk.
from 74 to
50.
yeah.
Sure, you can do chunks.
Is this getting to a certain term?
It's what?
So that's, say we want this number at the 13th term.
Well, right now we just want this sum right here. But yeah, that's a separate question I can ask, is I can say, Omar, what if I said to you guys, I want the sum of the counting numbers up to any number I say. Like, what if it was add the numbers 1 through 25? Tell me the answer. If it was 1 through 50, tell me the answer. Right now I just want 1 through 100. Does anybody have a way to solve it?
I don't really solve that. Is this anyway similar to the rational root theorem?
Not that I know of. But maybe. Okay, so folks, are you ready? This is how Gauss did it. And in fact, this is how we do it in this class. So Gauss looked at this and he said, buddy up the first and the last number, because that's just 101. And then buddy up the second and the second to last number, because that also adds up to 101. And then buddy up the third and third to last number, because that's also 101. And they would all be 101. And how many pairs are there? It's 1 through 100, so how many pairs are there? 50. So it's really just 50 101s. And if you multiply 101 times 50, you get 5,050.
But he's a first grader, right?
Right, but he was a first grader, so that's still pretty good. Yeah, it's very good. Anyway, so that's the clever little trick, right? And as it turns out, if you want to add up any arithmetic sequence like this, where it's just you're adding, here we're adding 1, we're adding 1, we're adding 1, we're adding 1. The sum of n terms is the number of terms divided by 2. So 100 divided by 2 is 50. Times the first term plus the last term. And that's what that means. A sub 1 means the first term, and A sub n is referring to the last term. And that is exactly the formula that he did. He did 50. So this was 100 divided by 2, which was the 50, And then the first term plus the last term, which was under 1. So the mental technique Gus used to solve the problem is actually the formula that we use when we find the sum of an arithmetic sequence. All right. You know what's super crazy about that formula? It doesn't even matter if I change it and count by something else. Like, what if instead of counting by ones, what if I changed it to 3, 6, 9, 12, 15, 21, 18. There. So now we're doing this, we're counting by threes. Now the fact is I can still do 3 and 18 is 21, 6 and 15 is 21, and 9 and 12 is 21. And how many of them are there? 3. So it would still be 1, 2, 3, 4, 5, 6 terms. So 6 over 2, 6 is the number of terms there are, first plus the last. And the formula works even though we're counting by a number other than just regular counting. You would still need to know how many terms there are, and that's the tricky part. But the fascinating thing is that the formula, you'll notice nowhere in here does the formula say what you're counting by. So you could be counting by 2s, counting by 4s, counting by 10s. Okay, so that's just a little teaser for you. You know, to hopefully I'm motivating you to be interested in what we're talking about. This next question is a really good one. We're asking what's the sum of a half plus a fourth plus an eighth plus a 16th plus a 32nd plus a 64th, all the way up to infinity. 1 is a very good guess. I would like you all to see as I type it into Google, because Google is a pretty good calculator too, by the way. I don't know if you know that. But if you go to Google, oh man, this thing is Google, and you type in 1. Okay, sorry, 1/2 plus 1/4. Brings up the calculator. So this is what I'm at so far. A half plus a fourth is 0.75. So now plus, and what do we do? Plus 1/8. Yeah, 1/8. Now I'm at 0.875. Plus a 16th, I'm at 0.93. Plus a 32nd, 0.96. Plus a 64th, 0.98. Plus a 128th.
Yeah, you're right.
Plus 1 256th. Plus 1 512th. Your guesses are kind of correct. Plus 1024th. And then plus 1 2048th. So you see we're getting close. Now we're at 0.999. So what is this number going to become if I kept doing this all day? So let's see, 4096, that's plus 18192. I wanted to get to another 9. I don't know what 8192 times 2. That'd be 16,300. 386 maybe? Hey, 4 9s, all right. So what is this answer becoming?
The Batman.
So when we do 1/2 plus a fourth plus an 8 plus dot 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 dot, we're approaching 0.99999. Now, on the calculator, no matter how long I do this, if it was a good calculator, would it ever bump up to 1? It's always going to say just below 1, right? Every answer, for however many you've typed in, the answer is still going to be below 1. But the question is, what if I did keep doing it forever?
You would never get the you would get an answer, just be never get
Yeah, see, philosophically, this is very tricky.
infinite 9.
I'm saying if you did add together infinitely many terms, what would the answer be? If you could add together infinitely many terms, then would it be 0.999999999 repeating, or would it be 1? It would be 0.99999 repeating. Okay, so that's the first answer that's true. It's 0.99999 repeating. So where on the number line is the number 0.999 repeating? Here's the number 1. Here's the number 0.9. So where's the number 0.99999? It's like here-ish? Well, how close is it?
All you have to do is round up.
Yeah, all you'd have to do is round up and you'd be there. But how close? Is it like right next to it? Like Emily is sitting right next to Valeria? But you're not even touching arms, so you're not that close. I mean, somebody else could come sit in between you. Yeah, so how close is it? Well, could you add anything to 0.999 and still be to the left of 1? Could you add anything to 0.999?
Talking about
Right, well, I've already added all infinitely many of them. So there's no more fractions to add in there. Well, I mean, unless you're just talking about some small fraction.
So never is gonna be one. That's good.
Well, yeah, on the one hand, this sum is 0.999 repeating in front of that. So I guess the next question is, do we think that 0.999 is to the left of 1, or do we think that it is 1? Is it to the left, or is it on? What do you think, Lloyd? Is it to the left of 1, or is it on 1? Emily? Hector?
I'd say it's all gonna be the left.
Omar? Well, all of you agree, Lee.
I feel like it's one now because
Because I'm making a big deal out of it. Yeah. Right, so now folks, what I'm about to tell you is honest truth, okay? I'm not messing with you. It's not a magic trick, it's not a joke. But it's a big question, and the question is 0.9999 on the 1, or is it to the left of the 1? So what I'd like to do is I'm gonna give you 3 different demonstrations for why it's actually equal to 1. So I'm gonna sit here and say to you, 0.999 is equal to 1. And the first thing I'm telling you is that I'm not winking at you while I do this. like 0.999 is equal to 1. Like it's just something we say, but not really, right? But we say it is. Because you know how sometimes someone might say 1 divided by 0 is infinity. Well, that's not really true, right? Because if I take, like just consider how somebody could mislead someone else. If I do 1 divided by 100, it's 0.01. But if I do 1 divided by 1,000 or something, it's 0.01. So if I do 1 divided by lots of zeros, it's going to be 0.01. Now, if I do 1 divided by infinity, what would you say it is then? Wait, I'm going the wrong way. I'm so sorry. I meant to be going the other way around. 1 divided by a small number. Oh, we want to divide by 0, of course. We want to divide by 0. So if I do 1 divided by 0.1, it'd be 10. 1 divided by 0.01 would be 100. 1 divided by 0.001 is 100,000. 1 divided by 0.01 is like a billion. So if I keep going this way, 1 divided by a number that's very small, well, that's a 1 with 16 zeros at the end of it. Essentially, somebody might fudge it and say 1 divided by 0 is infinity, because the numbers keep getting bigger and bigger. Oh my gosh, Google even says infinity. That's Google. It's wrong. It's not infinity. It's undefined. That should have said undefined. I'm shocked right now. I can't believe Google said infinity. Somebody should.
Google is an infinite itself.
Yeah, so definitely, folks, 1 divided by 0 is not infinity. 1 divided by 0 is undefined. So, what was I shooting for here? So the question is 0.9999 really equal to 1 or just something people say? Because people say 1 divided by 0 is infinity, but that's just something people say, it's not true. Okay, so folks, here's what we're going to do. I want all of you to take your pencils out. You got your line sheet paper or somewhere. A very valid mathematical technique is to say, what is 0.99999? I don't know what this thing is. Where is it on the number line? I don't know. Is it to the left of 1? Is it on 1? I don't know. In fact, I don't even know what this number is, so I'm going to let it be equal to x. Anytime you don't know what something is, you can just say let it equal x. What's that? It
Says on the right.
Oh, you're going to say it's to the right of 1? You're funny. Did anyone want to say it's to the right of 1? Okay, so when you don't know what something is, you can say it equals x, and the power of letting something equal x is that now you have an equation. And what can you do to an equation? Yeah, anything you want. You can do anything you want to an equation, so long as you do it to both sides. So watch, I'm going to multiply both sides by 10. So over here, 10 times this moves the decimal once, and I get 9.9. And over on the right, 10 times x is 10x. Now I have 2 equations. I could do elimination or, not substitution, but I could do elimination right now. And I'm going to subtract top minus bottom. So over here, what's 10x minus 1x? 9x. And over here, what's 9.999 minus 0.999? Yeah. What happens to infinitely many 9s? They all cancel out. And therefore, when we solve, It's definitely equal to 1. So 0.99 is not to the left of 1, it's actually on 1. Okay, one more thing to show you here. Let's say, what?
Okay, math whiz.
Yeah, well, I mean, it's not like I came up with this proof. But I want everyone to know that 0.99 is equal to 1. Here's another one. What is a third plus a third plus a third?
1. Because they all have the same denominator, so you just be adding the top and then just basically divide it.
So 3/3, and that's equal to
1.
1. Now, what's 1/3 as a decimal? 0.3.
Just repeating.
0.3, and 0.3. And what happens when you add all those 0.3s together? 0.99. And so what is 0.99 equal to? Definitely 1. So this is not like a tongue-in-cheek, it's equal to 1. It's equal to 1. And there are a lot of people who don't believe it, and they'll die before they would admit it. But it is true.
Why's that?
I don't know, because it's just so uncomfortable.
Is it, sort of, or documented, but like, you know how scientists, they do it's like the experiment or whatever, and they have the results, and then anybody can take those results and try to do it themselves.
Verify it?
Yeah, verify it. Are they able to do it?
Well, I mean, you'd think anybody could just sit down and do the things I'm doing right now.
I know.
But even then, they don't believe it. They're like, no, still, it's less, it's to the left, it's to the left. You know, they just keep saying it's to the left. Well, here's one more.
But it's not in a box.
What do I want to say? Yeah. So, here's the thing. Let's say I take a square, and I'm going to shade half of it. I'm going to shade half of it, and then I'm going to shade a fourth of it, and then I'm going to shade an eighth of it, and I'm going to shade a 16th of it. So watch as I go. I take my square, and I shade half of it. So that's my 1/2. More. So that's a half now plus a fourth, I'm going to shade this. So far I've shaded 0.75. I'm going to cut the remaining part in half again, and that represents 1/8 of the whole thing, and I shade that. Now, so far, how much of the square have I shaded? A lot, right? So the question is, if I keep doing this, shading half of shading half of shading half of shading half, will I eventually shade the whole thing?
Yeah.
You're all very quick to say, yes, I will.
No, I won't.
Because again, if I take half and shade it, at every step along the way, is there an unshaded portion? Yeah, but if I keep going forever and I do it forever, then will I shade the whole thing?
Run out of space eventually.
Yeah, I mean, we're kind of stuck saying, yeah, you're going to end up shading the whole thing. And you can make that very rigorous by saying, if you're going to make the claim that I'm not going to shade everything, then I should be able to locate a point that's not going to be shaded. Right? If you're going to claim that if you keep doing this forever, it's not going to shade the whole thing, it's still going to be a little bit unshaded, then you should be able to say, see that bone right there? You're never going to shade that spot. But what I can do is if I just keep doing this process long enough, I will eventually shade that point that you said I couldn't shade. And whoop, now I did it. And you're like, okay, we're fine, not that point, this point. And you choose another point. You're like, you're not going to shade that point. But if I just keep doing this process, I'll eventually shade that point too. So the argument goes, choose any point you like, I'm eventually going to shade it. And therefore, the entire thing is shaded in. So no matter what is this sum equal to?
Is there any way that you could just shade it to the point where like the part that's not shaded is so minuscule that it doesn't even matter?
Well, right, that'd be like you get to 0.999 with like 40 decimal places.
Yeah.
So any fraction like this is gonna be 1.
Well, not any fraction like this.
I mean, but
because-
it has 1 on top.
Well, right, if you do a third plus a 9 plus a 27 plus an 81st, that's going to get a different answer. Because then you're only shading a third, a third, a third, a third, a third. And in fact, that answer is going to end up being that sum adds up to 1.5. Now, it's kind of weird. Right? No matter what denominator you choose, it's going to end up equaling something, but not necessarily 1. But you can find the sum of an infinite sequence like this. Yeah. Okay, so again, folks, I hope that has interested you. Now, one more thing, just to round this off. Some people are uncomfortable with 0.999 equaling 1 because that's weird. There's 2 ways to write 1. Like, pay me $1. Pay me 0.9999999 cents. You know, they mean the same thing. But the point is, within the decimal representation framework, there's 2 ways to write every number. That's not so weird because within the fraction system, how many ways can I rewrite the number a half?
Several.
Several. A million. Infinite. Aren't there infinitely many ways for me to write the same fraction? Well, I'm just telling you there's 2 ways to write the same decimal, right? So I mean, that's very conservative. There's infinitely many ways to write the same fraction, and I'm just telling you there's 2 ways to write the same decimal. So for instance, 25 cents. 25 cents, you can write it that way, or you can write it this way. And both of those are equal. They are equal. So take any number at all. Now, Lydia, give me a number. Give me a decimal. No, okay, 35.9. That is equal to 35.899.
6 maybe.
Oh, but had you said 36, then I would say that's equal to 35.9.
999.
Yeah.
So everybody knows what to do, right, on the test? Except when an actual answer, put the 1 right before and then put 99999.
Yeah, exactly. Yeah, that's the rule. So like, take somebody's age in the room. Let's say you're getting sad about turning 40. And you're like, hey, I'm not 40, I'm 39.9999. And the fact is that's equal to 40, but it makes you feel better about yourself so you don't cry at night. Right? Okay. Well, folks, again, this is fun. See, I hope you think this is fun. All this is fun.
Question.
Yeah.
For your elimination, how does that equal 9.99?
I subtracted, not added.
Oh,
You're allowed to subtract or add. Furthermore, I didn't have to subtract. I could multiply both sides by a negative and then add. So either way, it's 9 equals 9. Does that answer your question?
I'm thinking the difference is so we call it the elimination thing. So if you did it by negative, then they would both have to be negative 9.999 equals negative 10x.
Yeah.
Which makes it undefined.
If you got negative 9.99 equals negative 10x.
Yeah,
And then what's the second equation?
9.99.
Oh, well, if you do 9.999 equals 10x, and then you do elimination on those, they both cancel out and you have 0 equals 0. That's just unhelpful. It's not undefined. It's still true. 0 equals 0 is true. It's not undefined. Yeah. The main thing here was, and Omar, we can do it with anything. Just take 0.333. What if I was like, what is that equal to? Well, that's not going to work.
What if we're doing this? What if we're doing this kind of problem with square roots?
Yeah, right. I mean, you could ask something similar. You could say, what is the square root of 2? And then you could say, well, I don't know what it is, but if I square it, it equals 2 exactly. Yeah, there are actually some systems in math where instead of talking about a number like the square root of 2, they just say, there's a number that has the property that when you square it, it equals 2. And that way you never actually have to talk about square roots. You're just talking about a number that has the property that when you square it, it equals 2. And then you never have to write down the square roots in it. Kind of weird. Okay. Well, folks, that was a nice little chitty chat that we just had. So those are some things that you can do with sequences and series and why they're interesting. So let's take a look at the top of 9.1. And what we're going to do is learn about vocabulary and notation and how we talk about sequences. So everybody has it? So a sequence is a list of numbers or terms which are related to each other by a rule. You need a rule. And these 7 examples, it says write out the first 4 terms in the sequence. So all we need to do is write out the first 4 terms in the sequence. But first, let's understand how we write out a sequence. So when we write out a sequence, if you don't know what the numbers are, we use the letter A and subscripts. So the first term is A sub 1, second term is A sub 2, third term is A sub 3, fourth term is A sub 4, and so on. So we will use the letter A, although you will notice that some problems use the letter B. Ultimately, it doesn't matter, but A is the tradition. We use the letter A with a subscript to describe the terms in the sequence. Now, at some point, if you keep going, you'll get to like A sub 100. Right? So that's the 100th term. But if you wanted to keep going even beyond that and just say, I get to some term, I don't know what the term is, I'll call it A sub n. And now you're just saying that's the nth term. Okay, that's the third term, fourth term, 100th term, nth term. And that just allows us to speak about any particular term. And all you'd have to tell me is what n value you want, like n equals 200, and we'd be talking about the 200th term. So when we talk about A sub n, you're just waiting for someone to say, let n equal 237. And then you'd be talking about the 237th term. Okay, so now let's take that a sub n. What if I'm looking at the term a sub n, and I want to look at the term right after it? What would the term right after it be? Yeah, a sub n plus 1. Write this down too, folks. So you've got all that in your notes, but now also the term after a sub n is n plus 1. So a sub n is called the nth term. Nth term. Boy,
And metal.
nth what?
And metal. I'm also good.
Oh, okay, sure. So that's the nth term. We would refer to a sub n plus 1 as the next term. Yes, the next one. What's the term after that? A sub n plus 2. And that's the next one. Which, by the way, I think I read online that if you're talking about this Wednesday, you say this Wednesday. That's 2 days from now. But if I went next Wednesday, it'd be next Wednesday. But the Wednesday after that would be Oxt Wednesday. I think I've heard this. Ox Wednesday.
So it's worth.
Right, because I think if I said this Wednesday, everyone knows I'm talking about 2 days from now. Whereas if I say next Wednesday, I'm not talking about this Wednesday. I'm talking about next Wednesday. Whereas if I want the Wednesday after that, I would say Ox Wednesday. This is just what I've read online. I don't know if it's true or not. But somebody suggested or is saying that's going to be the word that means the one after that. But if I want the next one, just tell me the date. May 4th, you know? Let's not get crazy. Okay, so that's the next term. What about the term before the nth term? What would that one be?
Minus 1.
Yeah, a sub n minus 1. And we call that the previous term. Okay? So this is how we refer to things. And in fact, the term before a sub n minus 1 is a sub n minus 2. That's the one previous. So this is how we label out all of our terms. And we're now in a position to talk about number 1. So in number 1, it gives us an explicit formula. This is an explicit formula. And the formula is a sub n equals 2 to the power of n minus 1, where they're only going to let us let n be greater than or equal to 0, and that's only whole numbers. So what can n equal? 0, 1, 2, 3, 4, 5, 6, 7, up to infinity. Okay, so let's go ahead and list out the first 4 terms. What would a sub 1 be? We're just going to let n equal 1. So we go over here and we'll let n equal 1. So 2 to the 1 minus 1 is 2 minus 1. This is called an explicit formula because any n value I plug in, I can calculate what the nth term is. So what's the second term? A sub n, I let n equal 2. 2 squared minus 1, that's 4 minus 1, that's 3. A sub 3, I let n equal 3. So 2 cubed minus 1, that's 8 minus 1, which is 7. A sub 4, I let n equal 4. 2 to the 4 minus 1 is 16 minus 1, which is 15. Again, it's called an explicit formula because now, choose any number. Choose a big number. Not that big. Okay, 5. I mean, that's the next one. What? Choose a number in the teens. 15. Okay. I'm
He's
sorry.
a big number.
Yeah, I'm being very specific. Finally, I'm like, choose 12. Okay, 50. Because I have to have a prayer of doubling it. So 2, 4, 8, 16, 30. Wait, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048. Oh, I can't even do that. Well, anyway, it'd be some very big number minus 1. Right?
Got the best students in the world.
Yeah, you guys are great. You're a lot of fun. So 2 to the 15 minus 1. Okay, so the actual answer is 32,767. So, by the way, explicit might feel like a weird name because what's the only time we use the word explicit?
Explicit content.
Explicit content, explicit lyrics, Tupac album, they use potty words, words you don't want your toddler hearing. So that's explicit.
It's crazy though, because nowadays, when there's some beforehand, the words they're using compared to what they're using now, or the body using TV and radio and music.
Yeah, we use a lot more bad language nowadays.
Well, think about how it was 100 years ago.
Okay, so there's the first one, folks. Now that was one particular way of writing the nth term. So this formula right here, a sub n, again, that represents the nth term. This is actually a formula for the nth term. So now I know any term I like in that whole sequence. So number 2, now here's what I like to do. I know my phone just went off, but let's do a couple more examples because we're already in it. We'll take a break. Now they're telling us, here's a set of numbers of the form n squared plus 1 over n plus 1.
Okay,
Oh, wait, what?
We're looking at it.
Oh, no. Am I looking at the wrong thing?
Oh, no.
I guess that's three.
No, I'm looking at the wrong thing.
That's not three.
No, your two is our three.
Yeah.
Yeah, no, it's wrong. I just have the wrong.
I guess you're doing number three.
No, I'm gonna make mine match yours. I just don't know why it's not. Oh, I just fixed this.
Was that?
All right.
No, I forgot. Oh, there we go. I got it. Okay. Very good. The next one is actually the set of numbers of the form 5k minus 2. So it's the set of all numbers of the form 5k minus 2, where we're just going to let k take on the values from 1 to infinity. So what can k equal? 1, 2, 3, 4, 5 up to infinity. And they're numbers of the form a multiple of 5 minus 2. So if we now start plugging in, so our formula therefore, just written a little differently, is a sub k equals 5k minus 2. This time they're using the letter k. It doesn't matter. Sometimes they use the letter n, sometimes they use the letter k. In any case, we want the first term, it'd be 5 times 1 minus 2, which is 3. And if we want the second term, we plug in 2, so that'd be 10 minus 2, which is 8. If we want the third term, that'd be 5 times 3 is 15 minus 2 is 13. And so on. So the fourth term would be 5 times 4, which is 20 minus 2, which is 18. In both cases, what we could do when we're done is just write the list. Start writing down the list. So like my first list was 1, 3, 7, 15, dot, dot, dot. My next list is 3, 8, 13, 18. And from here, you can kind of tell it's going to 3, 8. So the next would be 23, 28, 33, 38. Very predictable. Hector?
What is the value representing the equation?
It means that that set keeps going forever.
Oh, okay.
That you're not going to stop at any point. You're considering the entire list. We're just going to do a couple more, because we're almost done with the explicit ones. So, in fact, the next one is the last explicit one. So, number 3, we're looking at the set of numbers of the form n squared plus 1 over n plus 1, where n can go from 0 to infinity. Now, again, this is interesting. We're saying, I want to consider the whole set of all the numbers that have the form n squared plus 1 over n plus 1. So we're looking at a set of fractions. And what are the numerator and denominator of those fractions? They're calculated by plugging in the numbers and seeing what you get. So if we let n equal 0, we get 0 squared plus 1 over 0 plus 1, which is 1 over 1, which is 1. So the first term of that sequence is 1. If we let n equal 1 now, because we're starting at 0 and counting our way up to infinity, so that'd be 1 squared plus 1 over 1 plus 1, which is 2 over 2, which is still 1. Now notice right here that if I had simply said, hey, I'm thinking of a pattern, and it goes 1, 1, what's next? I mean, yeah, your best guess would just say 1, right? But notice that if you didn't know the formula and I just said the first two numbers are 1s, the next number could be literally anything, because you have no idea unless you had the formula. But now let's go ahead and let n equal 2. So it'd be 2 squared plus 1 over 2 plus 1, which is 5 over 3. Well, that was surprising. The next term is 5/3. Who would have guessed it? Nobody. What about let n equal 3? Now, even though our index number now, we did 0, 1, 2, 3. This is still the first 4 terms. So now we'd have 3 squared plus 1 over 3 plus 1, which is 10 over 4, which simplifies to 5 halves. And again, as far as things goes, this is one crazy looking pattern. Like nobody would look at this and be like, ooh, I know what comes next. Not unless you knew the formula. Oh yeah, boy. If somebody just handed you this and said, come up with that formula from scratch, I don't think we'd have a prayer. Okay, so each of those, number 1, 2, and 3, are called explicit formulas. Because right now in all 3 of those, if I told you I want the 50th term, can you tell me how to find the 50th term? I would just plug in, well, in this case, 49, right? Because I started at 0, so the 50th term would be 49. So it'd be 49 squared plus 1 over 49 plus 1. And I would type that all in my calculator and I'd get some answer. So that's what explicit means. So let's take a break. The time is 1:37. Let's be back at 1:47.
The 500, with 5 over 2, is that our like last problem? Is that our last point?
Huh?
No, the first one. 5 over 2 is the last point, right?
That's it. Yeah, that's as far as we went.
Like, I used to have this like this. Well, yeah. ¿Cómo te llenan? No. Qué listo. No. Oh, it's a shame. No, I think I'm calculating on my I don't know. ¿Cómo está ya? Hay que saber. pensar. You know? I'm gonna annoy you every day. Okay, pero ¿cómo sabes eso? Respuesta.
So how was your business Easter?
Oh, good. Yeah, everything was nice. Thanks.
Oh my god. So weird how back then. And now. You're telling me cold. And that's okay. I'm pressing my hand. Can you do that? That was bad. Right. I love it. Like the cake and everything. Oh, like.
What was the joke for today?
Actually enjoy it.
I forget.
Okay.
I'll go up and look at it.
I was wanting to stop.
My friends surprised me with the birthday party. That was my the first and last time. Nobody asked this question.
Yeah, I was very lucky.
I hate my birthday. Because my mom always invites a lot of people. And I'm the one that ends up being the house, helping her with the everything. And it's my birthday. Hey, it's a,
I do
Is
stuff. I
that
do
the
stuff
first
for my birthday too.
really? I
I
do
had to
think
cut the grass on.
I want to enjoy my birthday. I want to like actually like lay back or at least help out. You know, like my siblings or stuff. And when it's their birthday, I'm like up vibing all together.
That way.
Well,
You
it's
said
okay.
siblings. Siblings. Older or younger?
My brother's 24. It's just my sister's 15. I did high school. I ended high school because I was in and I was never home. I was never home. It was funny because I like it. But I didn't use it for it was always like, oh, it was this. Oh,
So, like, there was only just one thing I was like, I just built like the actual body, like it up. I just built that up. I just do like this one more time. Then you got it out. Place.
I'm not bad.
Oh,
The only thing that I did
I was
I was just too afraid. I was like,
Oh, depends. We have to.
I'm nervous. I would also like,
If you do things, you have to think of yourself, see what you think. Work on like, start with that.
that's why I didn't speak for because my student council teacher was like, oh, it's so loud.
I'm not saying that. I'm saying you're too strong.
I'm just kidding. No, I am.
Yeah, fair. You could have done like a chocolate.
I don't know why I'm not next one.
Okay, but how can I put line?
All right, folks.
There.
Let's keep going. We are about to see something.
Really exciting. I think it's really cool. I think you're all gonna like it. Really? Yep. So first of all, the formulas I just showed you are called explicit formulas because you can explicitly calculate any term you like immediately. So if you want the 1,000th term, you just plug in the number 1,000 and bam, you have that term.
Is this the anti-life? Is it the anti-life equation?
Anti what?
Anti-life equation.
Anti-life equation, no?
Oh, okay.
But what we're about to see is something called an implicit formula. An implicit means you can only calculate the term after the one you know right now. So you have to go step by step by step by step, like climbing a ladder. So if you want to get to the 100th term, you have to do every single term along the way, and that's called implicit variance. I'm sorry. That's called the implicit formula. In my head, I want to know, wait a minute, what would implicit lyrics be? Like explicit means they're using body language. So what would implicit lyrics be like?
Like a nursery rhyme?
Yeah, like a nursery rhyme, or like implying you're going to use bad words, but then you don't, or you describe an album with implicit lyrics. What would that even mean? Right? Would Tupac do that? I don't know. We'll probably, I'm pretty sure this is somewhere. But all right, so implicit formulas. Let's look at number 4. Number 4, this is called an implicit formula because the only way, and I'll say it first, the only way to calculate the 5th term is if you know the 4th term. And the only way to know the 4th term is if you do the 3rd term, and the only way to know the 3rd term is if you do the 2nd term.
You can't cut it.
You can't cut it. Yep, you got to start at the beginning and go all the way through. So in number 4, it says that the first term is 3. That's like the seed at the beginning. And then they tell you that a sub n plus 1 is equal to a sub n minus 1. So what is a sub n plus 1? That means the next term is equal to the term right before it, the nth term, minus 1. So if we were to go ahead and just start making a list, okay, so we already know the first term, so the next term we need to know is the second term. So I'm going to plug in 2 for n. So that would be I have the first term, so I want the second term. So we're going to start by letting n equal 1. So if I let n equal 1, that'd be 1 plus 1. And if I let n equal 1, that's a sub 1 plus 1. So the first thing I did was let n equal 1. Notice there's a subtle difference between the term number and what we're letting n equal.
So if I plug in 1 for n, that'd be 1 plus 1 is a sub 2, and then plug in 1 of those is a sub 1. So now we can actually calculate what a sub 2 is. It's the first term minus 1. And the first term was 3, so 3 minus 1 equals 2. Now let n equal 2. That means if I plug in 2 here, 2 plus 1 is 3, so the third term is equal to, plug in 2, the second term minus 1. And in fact, let's just write this out for a little bit. If I let n equal 3, then what we're saying is 3 plus 1 is 4, so the fourth term is equal to the third term minus 1. And hopefully right now this pattern looks, understand what we're saying. If you want the fourth term, you need the third term. If you want the third term, you need the second term. If you want the second term, you need the first term. So the formula for a sub 5 is keep on decreasing. What? It does keep decreasing. So if you want the fifth term, you have to know the fourth term, and then subtract 1 from it.
So the first one is.
The first one they tell you. But yeah, so then go ahead.
It's A2 because.
I'm plugging in a 2 everywhere you see an n.
Okay.
So right there, 2 plus 1 is 3. But here, 2 is 2. Yeah?
Yeah.
Okay. Okay, so now let's actually find these things. If I want the third term as the second term, we just said the second term was 2, so 2 minus 1 is 1. If I want the fourth term, I need the third term. We just said the third term is 1, so 1 minus 1 is 0. If I want the fifth term, I need to know the fourth term. We just said the fourth term is 0, so 0 minus 1 is 0. So far our sequence is 3, 2, 1, 0, 1. Not very exciting. But this is an example of something called an implicit formula. The other word for implicit formula is recursive. It's called recursive. Recursive implies the word to recur, because you have to keep referring back to the previous terms to calculate the next terms. I'm not sure why else I use the word recursive. Maybe because you're using the same formula over and over. I'm not sure. Okay, so that's one example of a recursive formula or an implicit formula. Let's try number 5. In number 5, we're going to switch to the letter B. That's fine. B, so the first term in our sequence is a 2. And then they're saying B sub k plus 1 is equal to 3 times B sub k plus 1.
Also, k equals equal again,
Oh yeah, and k starts at the value of 1. So again, what we're saying is the next term, in order to get the next term in the sequence, you have to know what the previous term is, and triple it and add 1. And that's essentially, and just watch, I can just do it, right here. If I keep saying triplet, add 1, triplet, add 1, triplet, add 1. First I would triplet, 6, add 1 is 7. Triplet, 21, add 1 is 22. Triplet, 66, add 1 is 67. Triplet, 191 plus 1 is 192. And so on, you can just keep doing triplet, add 1, triplet, add 1. And that's what the formula says. It says take the previous term, triplet, add 1. So this is the sequence already, but let's fill in these numbers here, okay? We're saying first let k equal 1. So if I let k equal 1, then here I'd have 1 plus 1, that means b sub 2 is equal to 3 times b sub 1 plus 1. So the formula would be b sub 2 is equal to 3 b sub 1 plus 1. But
this is just for period. That's not significant.
how about
9, so 9 times b or k. What would that be? Plus
what if it was a 9? Yeah. Oh, I don't know. You would just have to start somewhere. You need a seed number. And then you just start non-tupling it at 1. Non-tupling it at 1. Okay, so again, without even calculating this, let's say I let k equal 2. Then everywhere you see a k, you let it equal 2. So 2 plus 1 is 3. So b sub 3. B sub 3 would be 3 times B sub 2 plus 1. Likewise, the fourth term is 3 times the third term plus 1, and the fifth term is 3 times the fourth term plus 1, and the sixth term is 3 times the fifth term plus 1. So you can see every time I'm referring to the term in front of it. Also, what you'll notice is that the whole thing is solved kind of like by unzipping it from the top to bottom. Like if right now I wanted to know B6, I can't actually calculate it because I don't know what B5 is. And if I wanted to know what B5 is, I can't do it because I don't know what B4 is. And if I wanted to find out what B4 is, I don't know because I don't know B3. If I want B3, I don't know because I don't know B2. And if I want B2, oh, actually I can solve B2. Because I can plug in 2 for B1, and so that'd be 3 times 2 is 27. Now I know what B2 is, so now I can calculate B3. 3 times 7 is 21. And now I can solve for B4 because I know what B3 is, so 3 times 22 is 66. And now I can solve for what B5 is because I know what B4 is, so 3 times 67 is 181, and so on. So we call this recursive or implicit. Number 6 is a kind of a silly question, but it's still nice to do verbally. Where they say the first term is 117, which is kind of a random number to start with. And then they're saying that the n plus 1 term is the reciprocal of the term before it. So it's the reciprocal of the term before it. So let's take a look. We know what the first term is, it's 117. So I'd like to know the second term, which means I'll let n equal 1. So if I let n equal 1, that means 1 plus 1. So a sub 2 should be equal to 1 over a sub 1. Well, what was a sub 1? 117?
So,
Yeah, so that's what the second term is. So then what's the third term? If I want the third term, that means I have to let n equal 2. Right, so that's going to be 1 over a sub 2. So right here you could say, well, what's 1 divided by 1 over 117? And if you do it mathematically, it's a bit of a bummer because you have to sit there and say 1 divided by 1 over 117, which is 1 times 117 over 1, which is 117. But if you just say, what's the reciprocal of the reciprocal, it's the same as the original. So if we just say, the third term is the reciprocal of the second term. Well, the second term is 1 over 117, and the reciprocal of that is just 117. And it just goes back and forth. So we want the fourth term, that'd be the reciprocal of the third term. But the third term is just 117, so the reciprocal of that is 1 over 117. And this pattern just flips back and forth between the two. Not very interesting. Okay, number 7 is very interesting, and I hope you'll all be very entertained and informed by this next example. So first notice that we're using the capital letter F instead of the lowercase letter a or the lowercase letter d. Any guesses as to why we would suddenly switch to a capital letter? Because we can, that's for sure. This one is more important because it's more famous. This is kind of a classic amongst math problems. Like a classic, like the Mona Lisa is a classic painting in the Louvre in Paris. Well, this is a classic question in math. And you might even recognize the person this is named after. It's named after somebody whose name starts with F. Right? No. Fibonacci. Does anyone recognize the name Fibonacci? I don't know if Fibonacci was an artist or not, but Fibonacci
I think it was an artist, not
he's a mathematician. He lived in the 1200s, maybe in the 1100s too. He was publishing books in the 1200s, which was a while ago, and he wrote a book called Liber Abaci. And Liber Abaci is the book that popularized and brought Arabic decimal numbers to Europe. Do you know what Europe was doing before he wrote his book and brought the Arabic? First of all, what are Arabic numerals? Those are the Arabic numerals right there. So they're the numbers that we use today. But if you were alive in the 1200s, you wouldn't even know about those. How would you be doing math? Roman numerals. So before his book, everyone was doing math in Roman numerals. So 1, 2, 3, 4, 5, 6, 7, 8, and then 9, 10. Okay, so those are your numbers that everybody was using in Europe before this book. And so how would you add in Roman numerals?
That's not even his real name, it's his nickname.
Yeah, it's what, Leonardo da Pisa?
Yeah.
Yeah, but we refer to him as Fibonacci. So how would you add? Well, what would 8 plus 9 be? Oh, this is a mess. Because you can't even add the 1 plus 1 plus 1 plus 1 to be 4, because the 1 is really 10 minus 1, which is 9. So this is a mess. Nobody, like math is harder to do with Roman numerals. You would kind of just have to think. Or maybe you'd say, well, instead of taking 1 away from x, remove 1 of each. Right? Because now I bumped 9 up to 10 and I reduced 8 down to 7. And now the answer would be 17. And that would just be the answer. Okay, so anyway, without going too much into Roman numerals, Roman numerals were harder to do, they were clumsy, and the Arabic numeral system was Arabic decimal system was far superior. And so starting in the 1200s, this book started becoming read, and by the 1500s or so, everybody was doing math in Arabic. Now, I just want you all to imagine this, okay? We don't realize that we are using this new technology that was introduced in the 1200s, because we just call this numbers. Like, we don't know that this is an advanced technology that we took, or, that we inherited. So just imagine, though, like, can you imagine someone doing math in Roman numerals? You'd feel sorry for them, wouldn't you? Like, of those cave people. Well, just imagine, though, couldn't it be that in maybe 500 years, in the year 2400, maybe we're not even using Arabic numbers anymore. Maybe we as humans have moved on to an entirely different number system, which is taught from kindergarten on, and the whole world uses it. Can you even imagine that? Can you even imagine that 500 years from now, we have completely ditched the Arabic decimal system and are doing math in a different way? I mean, doesn't it seem impossible to imagine? And yet, that's exactly what happened to them in the 1200s. They wouldn't have believed it.
Maybe it's not, maybe it is possible.
Of course it's possible.
It's the same numbers, it's more or less the same numbers, except the 0. More or less it's the same numbers. It's written in a different way. So you still be using the same numbers, it would just be in a different,
It'd be in a different form.
yeah.
Yeah.
What is
So-
0 in Roman numerals?
I don't know. Yeah, I don't know. I didn't think there was one. Okay, so, folks, so this is the book they introduced, and in this book, okay, he also had a problem about rabbits, okay? And so I want you to see this problem. Oh, wait, we should finish. This is named after Fibonacci. Let me finish. F is named after Fibonacci. Let's do this first problem right here. Everybody ready? If you want the nth term, you need the term before it and the term before that. So we already know term 0 and term 1, so what's term 2? I realize it's f sub 2. It's really the third term in the sequence, but it's f sub 2. So we would need f sub, if n is 2, minus 1 is 1, plus 0. So what's it? The first term, or f sub 1, is 1. And f sub 0, also 1. And therefore, f sub 2 is 2. So far we know that the pattern starts off 1, 1, 2. So what's f sub 3?
It doesn't exist.
What doesn't exist?
The 0 component.
Oh, in the Roman numerals. So what's f sub 3? Well, again, just using the formula, we're saying that the nth term is the one before it and the one before that. So the third term would be f sub 2 plus f sub 1. Right, you're just looking at the two terms right before it. So then the second term was 2. The first term was 1, and so this one equals 3. So far, if we just write this down, we have the sequence 1, 1, 2, 3.
So it's just basic math.
It is just basic adding. And in fact, we can ditch all these formulas now and just give you a conceptual understanding of the Fibonacci sequence. You look at the first two numbers and add them together. So 1 and 1 is 2. And then you do 1 and 2 is 3. And now you do 2 and 3 is 5. And 3 and 5 is 18. And 5 and 8 is 13. And 8 and 13 is 21. And 13 and 21, 4. 21 and 34 is 5. Okay, so that's the Fibonacci sequence. Now, what is the Fibonacci sequence? You add the two previous terms. That's it. Now, you might say, how could Fibonacci get famous for something like this? Well, first of all, he didn't. He got famous for this. Okay, he got famous for bringing Arabic numerals and the decimal system to us, to Europe. And by us, I mean the United States then inherited that because we were British, and the British got it.
Invented the harmonic system.
Yes, absolutely. This was from the Middle East. Oh yeah, the Middle East had great mathematicians. They did all sorts of great things while we were in the Dark Ages. They were doing real math. Okay, and again, we, I'm referring to the Europeans. You know, that's really silly to me because I'm white. I'm saying we because I guess my ancestors were in Europe, whereas if I was Middle Eastern, I'd be saying we were inventing the Arabic numerals, right? So we is very fluid in the way I'm speaking. I guess I'm speaking on behalf of Europe and how when they were in the Dark Ages, the Middle East was doing lots of really good mathematics, and then that mathematics came to Europe. Okay, so I'm speaking probably very incorrectly by saying we. It's a silly use of the word. Okay, so that's the Fibonacci sequence. Now, I'd like to see even more about this. This is just kind of fun cultural awareness of these number systems. First of all, so I wanted to show you the book. I remember looking at the book, and it's because one day I went to the ASU library, and I went in just to find this book and look at it. And so here it is. Here's a copy of the book. It's blurry because I took the picture. So that's the book in the ASU library, Fibonacci's Liber Abaci, a translation into modern English of Leonardo Pisano's book of calculation. So yeah, Fibonacci is his nickname. And, oh, there we go. So here it is on page 404. The question says, how many pairs of rabbits are created by one pair in 1 year? Okay, so he's asking, how many rabbits would you have if you start with one pair of rabbits and then you let them mate and mate and mate and have more babies and have more babies and have more babies? So it starts off, a certain man had one pair of rabbits together in a certain enclosed place, and one wishes to know how many are created from the pair in 1 year when it is the nature of them in a single month to bear another pair, and in the second month, those born to bear also. Yeah, a little confusing to read it. And then he goes on to actually solve the math problem. But now let me show you a really good YouTube video so that we can all imagine what's happening.
Wouldn't you like to know how many bunnies or rabbits per hour on average are born into?
Yes, and in his word problem, he says that every time rabbits mate, they birth another two. So first of all, this whole word problem is a little weird because do you really want a brother and sister rabbit to then mate and have more bunnies?
Let's skip that part.
Yeah, so ignore that, and this is the question.
Fans, Jason Marshall here with a special look at the solution to Fibonacci's rabbit problem from mat150 episode 16. Here's Fibonacci's question. If two newborn rabbits are placed in a pen, how many rabbits will the pen contain after 1 year? To answer his question, Fibonacci wanted us to assume that rabbits always produce one male and one female offspring, that they can reproduce once per month, that they can start to reproduce when they are 1 month old, and that rabbits never die.
All right, so you can tell that the word problem is not exactly realistic, right?
The immoral rabbit person.
Yeah, it is very immoral, I guess you could say. So no matter what, the babies are going to be a male and a female, which can then, a month later, start having babies themselves. They can reproduce every month, which is remarkable, because that includes conception, growing the baby inside, and then birthing it. And not just one baby bunny, but two baby bunnies. And then that's the word problem, okay? So let's watch their little
So
visual.
that's the question. What's the solution? Well, let's think in terms of how many pairs of rabbits are in the pen at the beginning of each month, starting with the one newborn pair in the pen at the beginning of the first month. These newborns are too young to reproduce, so we begin the second month with one pair as well. It's the same pair, but they're now adults that are mature enough to mate. As a result, one new pair of rabbits is born at the end of the second month. So at the beginning of the third month, we have a total of 2 pairs. The original pair again mates at the beginning of that month, but the newborn pair offspring. So at the beginning of the 4th month, we have a total of 3 pairs of rabbits.
Okay, so you see the little tiny arrows, they're tough to see. So this baby pair of bunnies becomes an adult pair of bunnies 1 month later. At the end of that month, you see the dot, dot, dot. This adult pair of bunnies just stays an adult pair of bunnies forever, just being an older bunny and continuing to mate every month, okay? Whereas this pair of bunnies gave birth to baby bunnies, and you can tell those baby bunnies are smaller, right? They're smaller in size. So right now they're just babies, they can't mate. So by the time the next month rolls around, those baby bunnies have become adult bunnies, but they didn't give any birth to any more babies. Whereas this pair stayed the adult pair, but they also did give birth to another pair. Okay, so that's where we're at so far. And you'll see the pattern. It goes 1, 1, 2, 3.
The original pair, their newest offspring, and their first pair of offspring, which are now adults. 2 pairs can now mate, and they each produce yet another new pair, giving a total of 5 pairs at the beginning of the 5th month. Now, 3 pairs can mate, so after the 3 new pairs of offspring are born, our total moves to 8 pairs. At this point, the sequence is 1, 1, 2, 3, 5, 8. What's the pattern? What's the pattern? The trick is that each number in the Fibonacci sequence is obtained by adding together the previous 2.
Okay, so that's enough. Now, you might be wondering, what's happening right now, and why are we talking about this problem from a book in the 1200s? Well, one is because he popularized the decimals in Europe, so he's a very popular mathematician, and also because the Fibonacci sequence is quite popular. If you just type into YouTube Fibonacci sequence, you're going to see tons and tons and tons of videos about Fibonacci, and more importantly, about the golden spiral. Have any of you heard of the golden spiral?
Mandala.
Yeah, if you see, the golden spiral is this particular design which is particularly beautiful and asymmetric, and Fibonacci sequence has to do with it. You'll see lots of videos. One I highly recommend to you is any video by Vhart. Vhart is very fun. Her videos are a little spastic. Like you can see how the way she is drawing all super fast, like the video is on high speed. Yeah, I don't understand how that works exactly, but Vhart makes some really nice videos. This is video 1 of 3 about the Fibonacci sequence. So she really likes drawing and she likes demonstrating things. It's well worth watching. If I were you, I'd go home tonight and watch Vhart's videos. It's called Doodling in Math, Spirals, Fibonacci, and Being a Plant. I think it's pretty good, and it would definitely show you, a little bit more.
Word popular. So what if a mathematician created something that was correct, but never got popularized?
Yeah, I know.
We would never use it.
It just would be used infrequently, I guess. Okay, so that's one thing you could watch. What else did I want to say here? So the Fibonacci sequence, watch some videos about it, the bunny rabbit problem. So now, folks, are you ready? I'm going to show you an adult piece of humor. And by adult, I just mean you have to know math in order to appreciate it. This is brilliant. So watch. Now, first of all, have any of you heard the phrase breeds like rabbits?
Yeah.
They breed like rabbits. What does that mean to breed like rabbits?
Multiply. Yeah.
It means to multiply quickly and have lots and lots of kids, right? To breed like rabbits. Have you all heard that phrase? Some of you raised your, okay. Some of you nodded your head. So any of you familiar with Disneyland and Fantasia? Do you remember Fantasia?
Yeah.
Fantasia was this thing that they did at Disneyland at nighttime, where you would go, and there's this huge display at nighttime. It was right there on the water, and there'd be music and a show. So anyway, that's Fantasia. Now, years later, okay, there was a boat, a dragon breathing fire. It was all alive, right? It was amazing.
Is this going to be watered down?
No.
Okay.
Okay, but then they turned it into a cartoon, and perhaps you remember Fantasia is the Sorcerer. It was a fun cartoon.
Amazing. The money I said, I gotta get spotted.
Come on now, there we go. So do you remember this cartoon from your childhood? Again, it was a combination of Symphony, but then also The Apprentice, Mickey Mouse. There you go. There's this whole scene where Mickey Mouse is the apprentice to a magician, and then Mickey Mouse borrows the hat, and he starts doing magic, and the broom, wreaks havoc. Anyway, maybe you remember this, maybe you don't. But Fantasia is an overall long cartoon, and there's a particular scene of it that includes Noah's Ark.
I bet you have no idea who was the name of Mickey Mouse's instructor.
I don't. Is it really Hector?
No, it's Jensen.
Oh, Jensen.
Yeah, Master Jensen.
Oh, okay. I didn't know that. Okay, so folks, everybody watch very closely. Again, children would not understand this, but you will understand it. So here, this is the end of Fantasia, and Donald Duck is leading all of the animals off of Noah's Ark. In case you're not familiar with Noah's Ark, it was a big boat that was built before a flood, and Noah took animals onto the ark to save their lives, and he took 2 of each animal. 2 of each animal, why? So that they could procreate, right? So they're going to get on the boat, there's going to be a massive flood, everybody on dry land is going to die from the flood, but all these animals in the boat will be saved. And so now here they all are leaving the boat. They've only been on the boat for a couple months, folks. My understanding from the Bible is that they're on the boat for maybe a month, maybe 2, right? Am I right? Does anybody know? It's not very long. Okay, so here Donald Duck is ushering them off. Everyone watch closely. 2 hippopotamuses. Now, did you see?
Yes.
That's hilarious, right? That's hilarious adult humor. I'm going to show you one more time. The 2 original bunnies and all the other bunnies after. See, that's wonderful. That's wonderful that that's in a children's cartoon. Right? And how many people do you think noticed that? Not a lot.
No.
Disney's known for that. They like hide stuff.
The same joke.
Yeah.
The same joke was in the recently made movie Zootopia.
Oh, but about breeding like rabbits?
Yeah.
So, I mean, who knows where that phrase comes from? It could go back to Fibonacci's problem because it's talking about rabbits breeding. Now, do rabbits actually breed that way? Probably not that exact way. But that's the Fibonacci sequence. Anyway, folks, that's it. I hope that you enjoyed that little cultural excursion. Now you know what the Fibonacci sequence is. There is one more piece to the Fibonacci sequence if you're curious. And again, I hope you go watch that video by Vhart, Doodling in Math Class. And that is, oh geez, I wonder if there's a website that will just show it. You know how there's a couple important numbers in that? Well, there's a lot of important numbers in mathematics, but you have pi, which is 3.1415, and you have e, which is 2.7182. We've seen that. Well, there's also a number called phi, or phi. And phi is 1.6180, something like that. And that's called the golden ratio or the golden spiral. And the whole idea is that if you made a rectangle whose length was 1 and 1.618, or more specifically that number, which is really 1 plus root 5 all over 2, I think. So if you take a rectangle like that and cut off a square, so here's my square, 1 by 1, cut that off, now I have another rectangle. Cut off another square from it, now I have another rectangle. Cut off another square from it, now I have another rectangle, cut off the square, cut off the square, cut off the square, and then you go like this, and it's the beginning of the golden ratio, or the golden spiral. So, the Fibonacci sequence, if you go out far enough, so you keep going, that'd be 89, that'd be 144, and then that'd be, oh gosh, 233. You take any given term and divide it by the term in front of it. So, let me go back to Google here. So if I start at the beginning, 1 divided by 1 is just 1. That's not very interesting. Wait, 1 divided by 1 divided by 1. But then 2 divided by 1 is 2. 3 divided by 2 is 1.5. 5 divided by 3 is 1.666. So remember the goal is 1.618. So then if I do 8 divided by 5 is 1.6. And 13 divided by 8 is 1.625. And I can't even see my own numbers. 21 divided by 13. 34 divided by 21, 55 divided by 34, what is it, 89 divided by 55, 144 divided by 89, is it 89? Yeah, and then 233 divided by 144. Anyway, well, bam, there you go. So that sequence of the Fibonacci sequence approaches the exact value of the golden ratio. Okay, folks, all of that was just to kind of show you some neat things in math. So hopefully you enjoyed it. Let's proceed. Are we on number 8? On number 8. All right.
Did we ever solve number 7?
What else was there to solve? We just had to write out the first 2 terms.
Yeah.
Okay, so let's go ahead and jot down these formulas up at the top. Maybe just write it down in your own words. These are the explicit formulas. Explicit formulas for an arithmetic sequence and a geometric sequence. So I'm going to write it down up at the top. So for an arithmetic sequence such as 5, 10, 15, 20, 25, 30, meaning you're adding the same number over and over and over again. That's an arithmetic sequence. When you're looking at an arithmetic sequence, the number that you're adding over and over and over again, you call that a common difference. So in this case, the common difference is D equals 5. So that's an arithmetic sequence where you're adding the same thing over and over again, and that number can be negative. You can be subtracting the same number over and over again. But we can refer to that number as D. And if you have such a sequence, the explicit formula is A sub n plus 1 is equal to the first term plus the common difference times n minus 1. Now I wrote that down slightly different. Oh, wait a minute. I'm so sorry. Forget all of this. That has nothing to do with these 2 formulas up here. I'm introducing something else. Please do not pay any attention to those 2 formulas right there. I'm sorry, I thought I was looking at something else. In any case, this is still important. So if you're looking at an arithmetic formula, first you need to find how much you're adding every time, call it D. And then this is the explicit formula. And what that states is that if you want any term number, you know, the 100th term, you would need to plug in n that you're interested in, and the first term, as well as the common difference, and then this would be your formula. We might as well finish. So that was arithmetic. Let me do geometric. Geometric. In a geometric formula, such as 1, 2, 4, 8, 16, we're multiplying by the same number over and over again. So in this case, I'm multiplying times 2, multiplying times 2, multiplying times 2, multiplying times 2. And so we call that the common ratio. Is R. Sorry, the common ratio here, the common ratio would be R equals 2. Okay, so this is just vocabulary. And the explicit formula for a geometric sequence is a sub n plus 1 equals a sub 1 times r power of n minus 1. I guess I didn't need to give you those formulas yet because they're going to give us the formulas on the next page. What we really needed to understand is just that there's something called the common difference and something called the common ratio. So in the next few examples, it says, determine if the given sequence is arithmetic or geometric or neither. For instance, the Fibonacci sequence is not arithmetic or geometric because you're adding the 2 previous terms. You're not adding the same thing over and over. If it's arithmetic, find the common difference D. If it's geometric, find the common ratio R. So let's start with number 8. At number 8, we're considering the set of all numbers that are of the form a multiple of 3 minus 5. And we're going to look at all the values from n equals 1 up to infinity. So we can start by just listing off the first few terms so we know what's happening. So let n equal 1. That would be 3 times 1 minus 5, which is just 3 minus 5, or negative 2. Let n equal 2. That would be 3 times 2 minus 5 equals 6 minus 5, which is 1. Let n equal 3. 3 times 2 is 9 minus 5, which is 4. And maybe one more for good measure. Let n equal 4, that would be 3 times 4 is 12 minus 5, which is 7. So what are we building here? Again, we're building the set of all numbers of the form a multiple of 3 minus 5. And I just listed out the first few numbers. So that's what's inside that set. So what is the common difference? What are you adding every single time? 3. We're adding 3 every time. Thus, D equals 3. And so it is an arithmetic sequence. Because we're adding the same number over and over. Now, how do we know for sure? What's that? Right, you can always just check, start adding 3 and seeing if it's that. If it's that. Another thing you can do is to calculate D, you take any term and subtract the term right in front of it. So this is what I wrote here. The nth term minus the term in front of it, n minus 1. So if I just start looking and I say 7 minus 4 is 3, and 4 minus 1 is 3, and 1 minus -2 is 3. And yes, I can verify that now. Take any term and subtract the term in front of it. It should always give the same answer. If it is always the same answer, that's your common difference, and the sequences are arithmetic. That's it for that one. So how about number 9? We're looking at the set of all numbers of the form 3 times a fifth to the power of n minus 1, where n can equal 1 up to infinity.
Just start with 1. So
Yeah, absolutely.
1 equals 0, so I guess.
So now, one good thing you could do here is we could make a table of values. Instead of continuing to write it down like we did, what do we make a table of values? And then we have our n value, and then this is 3 over 1 times 1/5 the n minus 1. We can start a table and say 1, 2, 3, 4, 5. And then we're going to plug in our value for n. So the first one would be 3 over 1 times a fifth to the 0. Well, what's anything to the 0? 1. So this is really just 3 over 1. So let's plug in the next number. That'd be 3 over 1 times 1/5 to the 2 minus 1, which is just 1. But I'm plugging the input numbers into our formula. So 2 minus 1 is just 1. And so that's just 3/5. Now we're going to plug in 3. 3 minus 1 is 2, so it's squared. So 3 over 1 times 1/5 squared. Well, how do we compute that? 3 times 1/5 squared. What do you have to do first by PEMDAS? Multiply or square? Square. So 1/5 squared is 1 over 25, because 1 over 5 times 1 over 5 is 1 over 25, times 3, so that'd be 3 over 25. Now, folks, in a situation like that, if it helps you, write it out. 3 over 1 times 1 over 5 times 1 over 5. That's 3 over 1 times 1/5 squared. So multiplying all the way across the top, 3 times 1 times 1, all the way across the bottom, 1 times 5 times 5. The answer is 3/25. You know, don't try to do something like that in your head if it makes you feel uncomfortable. Just write it down and do the computation. So the next one then, if I plug in 4, 4 minus 1 is 3, so cubed. So 3 over 1 times 1/5 cubed. Then you're going to cube 1/5, so 1 cubed is 1, but 5 cubed is 5, 25, 125. So that's going to be 3 over 125. And I think we've probably gone as far as we need to see what's happening.
Just try to be multiplied by 5.
Well, anytime you are multiplying by a 5 somewhere, you're not multiplying by 5, you're multiplying by 1/5. So let's look at our sequence, folks. Our sequence is 3 over 1, 3 over 5, 3 over 25, and 3 over 125, and so on. So when you're looking at a sequence and you think it's geometric, meaning you're multiplying by a number over and over again, you can just analyze the numerator and denominator separately. And you can say, I think my common ratio is a fraction. So what am I multiplying by? Well, first look on top. What am I multiplying by on top? I'm not multiplying by 3. How do I get from 3 to 3? I multiply by 1 times 1 times 1. So my common ratio will have a 1 on top, because that's what I'm multiplying by on top. What am I multiplying by on the bottom? times 5. So the 5 will be in the denominator. And so our common ratio is 1/5. Now I suppose the 1/5 is kind of obvious because that was the formula. The formula says to take the number 3 and take it and multiply it by 1/5 over and over and over and over again. So each next term of the sequence, you've multiplied by 5th one additional time. Like look, this term you haven't multiplied by 1/5 at all. Then you multiply by 1/5 once. Then you multiply by 1/5 twice. Then you multiply by 1/5 3 times. So each time you're just multiplying by 1 more 1/5. Okay, so yes, for sure, this is a geometric sequence. The common ratio is 1/5. One more thing, folks. In order to prove the common ratio, just like before I said the common difference is the nth term minus the term in front of it, the common ratio is the nth term divided by the term in front of it. That's just a quick way to find out what the common ratio is. You take any term and divide it by the term right in front of it. So let's try it. Take any term, 3, 1, 3, 1. Well, how do I do 3 1/25 divided by 3 1/25? You multiply by the reciprocal, so that would be 3 1/25 times 25 thirds. What happens to the 3's? Yeah, they cancel. And now I just have 25 over 125, which is 1/5. So what I just gave you is really important. You should write it down somewhere and have it in your notes. If you want the common ratio, take any term and divide it by the term in front of it. That's the common ratio. If you want the common difference, take any term and subtract the term in front of it. That's the common difference. That is if you already know that it's arithmetic or geometric. If you don't know that yet, you have to check every single one. All right, we're coming up here to some really good problems. It's going to be a lot of fun. I know you guys are already having a lot of fun. Nadine, most of all. Nadine, are you having fun? Oh, good. All right, so the next term. Now, this is where it's a puzzle. And this is not that hard of a puzzle. We'll see ones that are a little bit tricky. So what are we doing to get from one term to the next? Yeah, do we all agree that you're multiplying by 1/2? Analyze the numerator and denominator separately. What are you multiplying by on top? Yeah, you're multiplying times 1. What are you multiplying by on the bottom? 2. So the common ratio is 1/2. And that's it. That's the end of that whole problem. So this is geometric, and the common ratio is 1/2. Make the marker darker. Hi-ya!
You need markers?
No, I think this is enough. I like how Hector said to make it darker.
Oh.
Squeeze it. All right. So in this whole section, we're really only ever talking about arithmetic and geometric sequences. So let's see, like, what's number 11? Is it arithmetic or geometric? Are we adding the same number over and over, or are we multiplying the same number over and over? Yeah, we're adding a negative, we're subtracting, and what are we subtracting by? Yeah, minus 12. So every time we're subtracting 12, so we already know it's arithmetic. The common difference is negative 12. And again, to prove it to yourself, you would take any term and subtract the term in front of it. So I'm going to take negative 19 and subtract the term in front of it. And negative 19 minus negative 7 is negative 12. So indeed, that is the common difference.
I think the next one is 22 plus 2. You're multiplying by 10 and then add 2.
Maybe. Common difference is kind of funny. Like if I was like to my wife, our common difference.
Yes, and I call you teacher.
Yeah, this is ironic, right? Like jumbo shrimp. Like how can shrimp be jumbo, jumbo shrimp? What's a common difference? A difference you have in common? What is the difference? How can you have a difference in common? If our difference was I like rap music and she likes classical, how can you make that a common difference? I don't get it.
Don't like music?
Yeah, I suppose. Okay, so number 12. 222, 222, 2,222. Now the first question is, you can check both hypotheses and just try adding and then try multiplying. And again, you have to try the one in front of it. So if I take any term and subtract the term in front of it, that would be that the common difference is 20. But if I take this term and subtract the term in front of it, that would tell me my common difference is 200. If I took this term and subtracted the one in front of it, that would tell me my common difference is 2,000. And all of these are different numbers, so no, this is not arithmetic. It's not an arithmetic sequence because I'm not adding the same number over and over and over again. Here I added 20, and here I added 200, so no, it's not arithmetic. Now what about geometric? Is it geometric? What am I multiplying by? Yeah, well, and even if you tried to multiply and then add, that wouldn't strictly be speaking a geometric or arithmetic sequence. It could still be a sequence, Omar. I think you're right. In fact, I think you're totally right. The sequence would be times 10 plus 2, times 10 plus 2, times 10 plus 2, times 10 plus 2. What? Okay. Yeah, so, but that's not arithmetic or geometric. To be geometric, it's just multiply. To be arithmetic, it's just add. So if we now take any term and divide it by the term in front of it, 22 divided by 2 is 11, so R would be 11. But if I take 22 divided by 20, I'm sorry, 222 divided by 22, that would be R equals 10.09. And if I take 2222 divided by 222, that would be R equals 10.009. So no, it's not geometric either. It's not undefined, it's just a sequence that is not arithmetic or geometric. And that's okay. I mean, there's nothing too special about arithmetic and geometric sequences other than that they're easy to calculate about. The sequence times 10 plus 2 times 10 plus 2, you could probably still calculate things about that. There just aren't. It's not covered in this particular book. How about number 13? Is that something? Is that arithmetic or geometric? 0.99, 90, 900? What are we doing every time? Yeah, just times 10. Definitely times 10 each and every time, times 10. So this is geometric, and R equals 10. So again, we're just looking at sequences, trying to figure out what's generating the sequence. And if it's pure multiplication, we call it a geometric sequence, and we write down the common ratio. If it's pure addition, we call it an arithmetic sequence, and we write down the common difference. Okay. Now we need the explicit formulas for the arithmetic and geometric sequence. I wrote it down on the previous screen, but let's write it again now. So up at the top of the screen, and in fact, up above both of those, let's rewrite this one. Over here. So the explicit formula for arithmetic. Explicit formula for arithmetic. Let's write it down as a sub n equals a sub 1 plus d times n minus 1. You'll notice the book says n minus 1 times d. Why is it better to put d in front?
Because you can use it.
I think we're just used to seeing distributing numbers in front, not at the back. So it's just nicer to see that up front. What are you saying, Lee?
I'm saying because you already used A or alpha, so you don't want to use that again.
Wait, I'm asking why to put d in front instead of after.
Oh, okay, gotcha. Oh. Like that's why they use the actual.
Oh, okay, yeah.
Misunderstood, yeah.
Okay, so this is our formula. Let's try it once. Number 14 is an arithmetic sequence, and it goes 3, 5, 7, 9. So what's the common difference? Plus 2. What's the first term? 3. So we know now that the first term is 3, and we know the common difference is 2. So we can go ahead and use our formula and just plug in what we know. So the nth term is the first term, 3, plus the common difference, 2, times n minus 1. Now, folks, notice in the formula, all you're ever going to substitute for is the first term and the common difference. A sub n is kind of like the function name. You're calling that this is the nth term formula. And n is the number that you're getting to choose later on. Like, I want the 100th term, or I want the 50th term. So we take this formula now, and we just distribute. So 3 plus 2n minus 2. and combine like terms. That's 2n plus 1. So we call that the explicit formula for that sequence. Explicit because for any n value you choose, like you're like, I want the 11th term, you just let n equal 11, and it will tell you that term. Now, as soon as you write that down, we should probably verify that it even works for the terms we saw. So what's the first term? If I plug in 1, does it give me 3? Yeah. If I plug in for the second term, if I plug in 2, does it give me 5? Yeah. If I plug in 3 for the third term, does it give me 7? Yeah. Yeah, so the formula does work. The formula gives us the terms we already have, and the formula will give you any term later on as well. Well, that's it for the arithmetic sequence. There was just one example they gave in terms of using that formula and plugging numbers into it. How does everybody feel? We have 10 minutes left. We're going to get through a couple more problems, and we'll call it a day.
I really want to go on this.
Well, we're going to get one number 12 is. Number 12.
Oh, we never figured out what it was. We just it's either.
Yeah, it's just neither. But we did say that it's times 10 plus 2 times 10 plus 2. So it would be dectuple plus 2. Dectuple plus 2. If dectuple means times 10. For 15, we need an explicit formula for a geometric sequence. The explicit formula for the geometric sequence is that the nth term is equal to the first term times r to the n minus 1. That's the explicit formula for a geometric sequence. So first we just need to look at our sequence, 1, negative a half, 1/4, negative an eighth. And we need to figure out what is the common ratio. Yeah, it's negative 1/2. 1/2 because as we go from one term to the next. Now, by the way, how can I rewrite the number 1? Yeah, 1/1. So on top, I'm multiplying times 1. On bottom, I'm multiplying times 2. But the signs are alternating, plus, minus, so that means I must be multiplying by negative 1. So our r is negative 1. So now we just plug all that in. Again, you're only substituting for the first term and the common ratio. So my nth term is the first term times the common ratio to the n minus 1. And honestly, since that first term is a 1, you don't even have to write it. And you could just say the nth term is negative 1/2 to the n minus 1. And that is the explicit formula. So if all of a sudden, let's see, this is the first, second, third, fourth term. And then verify the fourth term, just to be sure. So that's negative 1/2 to the 4 minus 1 is cubed. And so that's negative 1/2 times negative 1/2 times negative 1/2. And a negative times a negative is negative, and 2 times 2 times 2 is 8. So what is the fourth term, negative 8? 1/8? Yeah. And furthermore, now we can find any term. Okay, so that's the formula, the explicit formula for a geometric sequence. And again, what you want to know is you're only ever substituting for the first term and the common ratio. You leave n minus 1 just like it is. You leave a sub n just like it is. Okay, we have time for 2 more problems. I'm really glad that we can do these 2 more problems. They're both really good. Oh, yeah. So, number 16. We're ending on a high note, folks. The sequence is 1, 1/4, 1/9, 1/16. Who knows the next term? Now, first of all, before you say anything, do you recognize the numbers 4, 9, 16? Do you recognize them? It's like you'd recognize a friend in the street. I would hope that you'd say, oh, 4, 9, 16, those are my friends. They're oh yeah, that's right. Yeah, the answer is yeah.
1, 6, 4 squared is 16, 9. That would work. So I was thinking 27.
Okay. No, the next one's not 27.
Is it 81?
The next one's not 81.
I'm thinking of as many numbers would be plus 3, 5, plus
Oh, now that's certainly, now first of all, folks, what should I do with that first one? 1/1, right? We want everything to be a fraction so it's consistent. And now that's true. If you're looking here and you said +3, +5, +7, that's why I almost said odd numbers. And so if you did do +3, +5, +7, what's the next one? +9? And 16 + 9 is, you know, that's certainly true. You can think of the formula in this way. But there's a different way to think of it. Who are these numbers 4, 9, 16, 25? They're not prime. They're squares. There are square numbers. Everyone do this with me. Take your sequence, rewrite it. It's 1/1 squared, 1/2 squared, 1/3 squared, 1/4 squared, and 1/5 squared.
That's what I was like.
Now, what we want is to come up with a formula for the sequence. It's not going to be the geometric formula or the arithmetic formula. It's just going to be a formula. So I want you to notice that the first term is 1/1 squared. The second term is 1/2 squared. The third term is 1/3 squared. The fourth term is 1/4 squared. The fifth term is 1/5 squared. So what would the nth term be?
1/n squared.
Yeah, exactly right. 1/n squared. And I hope that structure made that very clear to your brain. That the fourth term was 1/4 squared, and the fifth term was 1/5 squared, so the nth term would be 1/n squared. And so that's it. Our answer is a sub n equals 1/n squared. That's our explicit formula.
Could you do either?
What?
Could you do like either one? Like continue with the odd number to the top?
Yeah, it's tough because it builds on the previous one. You'd have to somehow come up with a formula.
Say you did it, you the national would be +11, 36, 36.
Right, yeah, I mean, it absolutely still works, but it would have to be a recursive implicit formula, like a sub n is equal to 1 over the previous term plus the next odd number. I think that's what it would be, but it would be very awkward. It's certainly not as good as just 1/n squared. But you could do it, Omar. You could. Okay, so there's that one. Let's try one more, I think. Let's see what time it is. Oh, it's 2:49. I don't think we can do another one. Folks, did you like the Fantasia video with all the rabbits? Was that cute?
Yeah.
I think it's a nice piece of adult humor. And there I'm reappropriating the phrase adult humor to just mean something you only get if you're educated. Not like using bad words and watching an R-rated movie. Okay, well, we'll proceed from there next time, folks. We have one more day of this, and then your test is next week. Now, folks, I'll give you the practice test on Wednesday. You can already go online and find it on Canvas. So I hope that you're already going to go online, download the solutions.